Hey physics students, I'm going to give you some notes here about what is called an Atwoods machine. Sounds kind of scary. What does an Atwoods machine do? Well, it doesn't really do much. It's a way of kind of messing with gravity and taking a couple of different masses and getting different accelerations. So there's a full-on Atwoods machine is something that looks like this, where this is a pulley and there's some kind of string going across it, and there's a couple masses. There's a mass here, and then there's a mass here. I tried to make that, I don't know how successful that was, if you can see that. That's a big M and this is a little m. So when we let go of this, what's going to happen? Well, if these two masses happen to be exactly the same, it would just balance. They'd just stay right there. And if you think that they would kind of like even out so they were next to each other, no, they wouldn't, because this one doesn't care about where that one is and vice versa. So if the masses are equal, then they're just going to stay there. There's no unbalanced force in either direction. What if they're not equal to each other? Then what? Well, I'm going to make that a little bit more obvious. This is a big M, this is a little m. So if you release the masses, if you're like holding them still, if you're holding onto one and then you let go, then common sense, I hope common sense would tell you that since this one is bigger, then they're going to start to accelerate like this. This one's going to accelerate down and this one's going to accelerate up. So how would you figure out the acceleration of this system? I'm going to do that for you right now. There's the hard way of doing it. It's not really that hard. Maybe like the more steps way of doing it, and then there's the fewer steps way of doing it. So let me show you the more steps way first, and then we can use to justify the shorter way, which it's fine for you to use. You still have to do a little bit of work, a couple steps to show. So anyway, I'm going to make force diagrams for the two masses, for the big mass and for the little mass. So here for the big mass, since these are going to be accelerating in this direction, the big mass is going to be accelerating down. That means the force of gravity on the big mass is going to be winning versus the force of tension. Right? And they're definitely not tied because this thing's going to be accelerating downward. And I know, I don't know what this mass is. I just made it a big M, so whatever that is times 10, that's how much gravity we got there. How about for the little m? Well, one thing I do know is that since this is the same string, it's the same force of tension on both of them. Now this one is accelerating up, so however much gravity there is must be less than that force of tension. Of course, however much gravity there is, that's not going to change regardless of whether this is moving or we're holding onto it or whatever. How much gravity is there? There's always 10 times little m on that. Okay, so the unbalanced force equation for this is winner minus loser. So that's the force of gravity minus the force of tension. I'm not going to put the 10m in there just yet. That's a g, sorry, g. And then mass times acceleration, that's big M times acceleration, is equal to the force of gravity is 10m, and the force of tension, I do not know what that is. I do know that it's smaller than this. That's going to be a positive number. Over here, I've got the unbalanced force here. On this side, tension is winning because this little block is going up. That is the winning direction, up, minus the force of gravity on that one. Unbalanced force here is little m times acceleration. Force of tension, I don't know what that is. And the force of gravity is 10 times little m. All right, now here's where the magic happens. You know from your math experience that you can take two equations and add them together, right? Like if you had an equation like 2 plus 7 equals 9, and then you have another equation that says 3 minus 4 equals negative 1, that you can add those equations together. 5 plus 3 equals 8, because if these things are equal to each other, and then you add on this and this, if you add this to this side and this to this side, well, these things are also equal to each other, so you're going to maintain that balance or that equality. So I'm going to use that little fact from math, and I'm going to add these two equations together. So here, when I add the left-hand sides together, I get big MA plus little ma. And then when I add the right sides together, here's where the real magic happens. Look at what happens here. I got a minus ft and a plus ft. Those are going to cancel out, which is great because I didn't know what they were equal to. So the fact that they're canceling out is good news here. And then I have 10m, 10 big M, minus 10 little m. And I'm going to do a little bit of factoring. Factor the a out here. It's a classic Algebra 1 move right there. You could factor the 10 out here or not. Doesn't really matter. I will go ahead and do it since I'm all fired up about factoring right now. Okay, so factor the a that these had in common and the 10 that these had in common. And then I'd like to know what the acceleration is. So the acceleration is 10 times big M minus little m over big M plus little m. So I did this with just like a big M and a little m, not knowing what the masses are. Typically, you're going to do this, you're going to know what the masses are. So you're not going to be doing it with m's usually, you'll have numbers. That is like the lots of steps kind of way of doing it. What's the sort of shortcut way of doing it? I guess you could say, well, the shortcut way of doing it, Mr. McGrath, is just to have this formula here and plug numbers into it. Yeah, but I don't want, that's not going to get you full credit. You got to show some work. Here's the shortcut way. If you've done this and you understand that those tension forces are going to cancel out, and it's going to happen. There's nothing magical about the way I set up this Atwoods machine. It's always going to happen because one side's got to be winning, like going one way, and the other side's got to be going the other way because they're attached to each other over the pulley. So that means tension's always going to be losing on one side and winning on the other side, so that they're always going to cancel, those tension forces, when we add the equations together. So if you know that, then you could just think about winners and losers here. So what's winning and what's losing? Well, here, the force of gravity on this is winning. So I'm still thinking Newton's second law here, but when I think about unbalanced force, I'm thinking about unbalanced force on the whole thing. So here, force of gravity on this, winning. So that is force of gravity on the big one, that's big M. And then force of gravity on this one, that's like tugging back the other way because we're doing this. So the force of gravity on the big one is in the direction it's moving. The force of gravity on the little one is opposite to that direction. So that's a loser. Loser. So this is my big M, force of gravity on the big one, minus force of gravity on the little one, right? That's the tug of war. This is winning, that's losing. And that's got to equal mass times acceleration. Well, what mass are we talking about here? Now we're looking at the whole system. So this is like the total mass. So I'm going to say m total times acceleration. So this is the shortcut way. This is what's winning. This is what's losing. Don't worry about the tension forces because I know that internal to the whole system they're going to cancel out They do every time. So here, what's the force of gravity on the big one? What's the force of gravity on the little one? What's the total mass? And then a tiny bit of algebra going to get you the same result. So it's a little shortcut, right, from writing out all that. And this is fine. We know we can do this every time because the tensions are going to cancel out every time. All right, so let me give you a couple more examples here of some variations on the Atwoods machine. And you can add this to your notes. What about a half Atwoods machine? Pay attention to this. Your practicum coming up pretty soon is going to be a half Atwoods machine. What about the half Atwoods machine? Well, what is a half Atwoods machine? So a half Atwoods machine is where the pulley is connecting two things, and one of them is hanging off the edge here, and one of them's on a flat surface. So instead of hanging like all the way over, we got this kind of situation. So I'm going to call these M1 and M2. So you can do the long way and the short way, but you know the tensions are going to cancel out. So you can do the little diagram and everything if you want, whatever. But when you release this thing, if there's no friction here, let's say for this example, there's no friction, then you know that this is going to go this way, and this one is going to go this way, right? Okay, so what do we got with winners and losers here? Here, the only winning thing is tension, and we're not putting tension in if we're doing the shortcut thing, because we know the tension on this one will cancel with the tension on this one. So what about the gravity on M1? Well, the gravity on M1 is straight down. It's not in the direction of motion. So that actually doesn't help or hinder. It's not, none of that gravity is in this direction, right? So gravity, normal force, the only thing going on with this one is that it's going this way, and that's just the tension force. So when I do the total unbalanced force is equal to the total mass times the acceleration, then the unbalanced force here, it's only gravity on this block that's getting it done, right? The gravity on this block is, it's kind of holding it to the table there, but it's not, none of it is in this direction. It's not helping or hindering. So the unbalanced force here in the half Atwoods machine is just M2 times A. Sorry, the gravitational force on that. So that's 10 M2 times A. That's the force of gravity on that one. And then here, force of gravity is not, it's not contributing. So M total is still force of gravity on this is getting both of these moving now. So I still have to include M1 in the total. And what did I do wrong here? Unbalanced force, oh, sorry, unbalanced force, that's, should just be that, sorry, 10 times M2. And then if I solve for that acceleration, then I get 10 times M2, that's the gravitational force on this block right here, divided by the total mass. That's the shortcut way. There isn't really an official name for this kind of thing here. You call it like a partial Atwoods machine or something like that. A slanty Atwoods machine. And it's kind of like a variation on this one where this is on a slope here. Okay, so can we use this maybe, you know, I think I really probably should have written total. So total unbalanced force equals total mass times acceleration. And the total unbalanced force, once you allow for the tensions to cancel each other out, which they do every time, is just the force of gravity on that. Okay, so let's think about this one in that way. Now, the tricky thing about these slanty Atwoods machine is, depending on what the masses are and what the angle is, it could go either way. It could actually go this way, or it could go this way. Depends on what those masses are. So, geez, what you do about that? Well, you just assume that it's going to go whichever way seems more likely to you, and then if you're wrong, you're going to get, about your assumption, if you're wrong, you're going to get a negative acceleration at the end. And all that negative sign is telling you is like, hey, you picked the wrong way. It's actually going the other way. So pick whichever way you want, and then be careful with your math. And if you get a negative, it just means the other way. And the number is the same. You're just going to get negative correct answer. All right, so this, let's assume that it's going to go this way. This one's going to go down, and this one's going to go like this. Okay, so what forces, besides the tension forces, what forces do I have in that direction of motion? Here, total fun. Physics is totally fun. So total unbalanced force in the direction of motion, not including the tension forces, because I know they're going to cancel out every time. So here, gravity on this one is a winner. So that's 10 times m2. And then what about this? Well, I better make a little force diagram for that one. There's the force of gravity on it. Now, there's this part here, right? And then I know the tension force is going to be here, but I'm going to ignore the forces of tension here in the total unbalanced force because I know they cancel out every time. So what about this? This is in the, this right here is in the direction of the motion, right? That's a loser. That's like fighting against the motion here. So when I have minus whatever, it's minus this right here. Well, if that's my angle theta, that's here. That's the opposite to that. So it's the sine component of the gravitational force on this. So that's 10 m1 times the sine of theta. Now again, you're not going to be doing this problem with m1s and m2s and thetas. You're going to have actual numbers. But it's that part of gravity, the down the ramp part of gravity, the sine component of gravity that's going to be losing here. And depending on what the masses are, it is possible that that could be winning, right? If this is like a lot bigger, more massive, or whatever. So if I was wrong, I'm just going to get a negative answer at the end. Total mass is just m1 plus m2 times acceleration. So when you push these things around and you can factor the 10 out, you get something that looks a lot like, it looks a lot like this, right? 10 times m minus m over m plus m, except that because the losing one was on a ramp here, we had to multiply by that sine theta. Right? Okay, so when you do these, you are going to, most of the time, the vast majority of the time, you're going to be doing it with numbers. And the only other thing I need to warn you about is if there's friction, then friction is also going to be on the losing side, right? Friction always opposes motion. So when you do your total unbalanced force, you might have this minus this, and then minus whatever the friction force is. Of course, friction is not going to happen in this kind of Atwood's machine, right? But it could happen here or here.